Okay, so for your ammonia reaction, we are really interested in what we call the Haber process. So Haber process is ammonia formation. So ammonia, the formula NH3 gas, you have to know, is made from nitrogen gas and hydrogen gas. Okay, and when we write the equation, we write a reversible arrow because it's a reversible reaction. Remember, the equation doesn't go to completion. Okay, and the enthalpy change is minus 92 kilojoules per mole. Okay, minus 92 means it is exothermic reaction. Okay, so remember exothermic reaction, less energy is absorbed to break the bonds than released to form. So I have a small number, less energy is absorbed, then released to form. So small number minus your big number, you get a negative exothermic value. Okay, the conditions that we choose for Haber process, these are optimal to produce the most reasonable amount of NH3. Okay, they are optimal to produce the most reasonable amount of ammonia gas. Maybe it could be like economically feasible, or the time constraint is the most reasonable. Okay, so let's look at these conditions. Yeah, so before I continue, we will look at this yield of ammonia. Okay, so from this graph, can you see that the lower the temperature, the higher the yield? All right, so let's look at it. At almost 100 degrees Celsius, your yield is 100%. And 500 degrees Celsius, your yield is only about 20%. Okay, so the best temperature that we decide ultimately is 450 degrees Celsius. Why? Okay, so why is it that the lower the temperature, the higher the yield? Right, this is because decomposition of ammonia means my ammonia breaking back to hydrogen and nitrogen gas is being reduced, okay, at high temperature. Okay, so let's use this example. The forward reaction is exothermic. Just now, as we discussed, is minus 92 kilojoules per mole. So it's exothermic, it gives out heat. So the backward reaction, which is the decomposition reaction, is endothermic. It will absorb the heat. Okay, so high temperature, there's a lot of heat for it to be absorbed. High temperature, it favors the backward reaction. Okay, so my ammonia is being broken down. So low temperature favors the forward reaction, forming ammonia. Okay, repeat. High temperature, backward reaction is favored. Okay, because backward reactions absorb the heat. And my ammonia is broken down. Okay, so this will result in lower temperature, higher the yield. Okay, so however, if the temperature is too low, it will reduce the rate of your forward reaction. So it means if I choose 100 degrees Celsius, yes, maybe it will give me 100% ammonia, but it may take maybe 20 days, which is too long to produce this 100% ammonia. Okay, so instead of choosing 100 degrees Celsius, we choose a relatively high temperature to increase the rate of reaction, 450 degrees Celsius. Okay, so 450 degrees Celsius will be somewhere here. Okay, and then pressure, the pressure that we choose is 200 atm. Okay, so from this graph, the graph shows that higher the pressure, the higher the yield. So let's look at the pressure now, right? So at 500 degrees, for example, 500 atm, I will produce about 35%. 300 atm, I will produce about 25%. So it corresponds with the higher the yield, the higher the pressure, the higher the yield. Okay, and again, why is this so? Increasing pressures favors the forward reaction. So remember, my ammonia reaction is nitrogen gas N2 plus H2 give you NH3. Right, give me 2 NH3, 3 H2. So your forward reaction, when you increase your pressure, just now I got discussed, when you increase your pressure, reduce the volume, there is 4 molecules here. So when you squeeze 4 molecules, they tend to form NH3. And the backward reaction of ammonia forming back this, right, when you squeeze here, okay, hold on, right, yeah, when you squeeze here, right, you're only squeezing 2 molecules. So when you squeeze 4 molecules, there are more particles per unit volume, so forward reaction is favored. Okay, so increasing the pressure increases the forward reaction. Okay, the speed of the forward reaction will increase too. However, if I make the pressure too high, it is too costly to maintain because these equipments are expensive and it is also dangerous, right? High pressure could cause an explosion. So instead of maintaining at 500 atm, I maintain it at 200. So we actually have a graph that's somewhere like this, and this one will be the optimal condition. Okay, about 28% U of your ammonia. Okay, and then this reaction takes place spontaneously. However, the rate of reaction is still quite slow. So we will need a catalyst. And what's our catalyst? Ion catalyst. Memory work. We have to know this. Okay, catalyst speed up the reaction. How does it speed up the reaction? It lowers the activation energy. It does not affect the yield. So it does not increase the yield. Okay, if it will still produce 25%, but it will produce 25% at a much shorter time. Okay, so where do I get your reactants from? Your nitrogen gas and hydrogen gas. Where do I get it from? I get it from nitrogen. I get it from fractional distillation of air. Remember, air is 78% nitrogen and 21% oxygen. And there's the 1% others. Right, so all these gases naturally occurring, you capture it, cool it down to liquid, perform fractional distillation to get your nitrogen gas. Hydrogen, this is formed by catalytic cracking of long-chain hydrocarbons in petroleum. So petroleum is the crude oil that we dig out. Okay, and then these long-chain ones are low in demand. We will crack it under high temperature pressure to make short alkanes, alkenes, and hydrogen gas. Okay, ammonia uses. So ammonia, these are used by, we make it mainly for fertilizers. Of course, there are many other uses, but we use it for fertilizers as one of the main components under the learning syllabus. Okay, so fertilizers, they are actually made into nitrate, the NO3 minus or the NH4 plus. Okay, so fertilizers that contains ammonium nitrate, we call them nitrogenous fertilizers. Why do we need this? Because the N is needed for your plants to make proteins. Okay, that's all for your ammonia.